Welcome to Module 7. In this module, we'll be seeing how to use AstroImageJ, or AIJ, for analyzing the observation of exoplanet transits. In fact, we will be doing a step-by-step walkthrough using AIJ to analyze the transit of exoplanet WASP-12b. And we will do so using the actual images captured during this transit. AIJ is freeware software that was developed and is maintained by Dr. Karen Collins, and it's an all-in-one software package that can be used for everything from image calibration to aperture and differential photometry, as well, of course, as exoplanet transit modeling. The latest version can be found at the website that you see here, and we ask at this point that you pause the video, go to that website, and download and install AstroImageJ on your computer. We also ask that you go to the website astrodentist.com, where you will find a practical guide to exoplanet observing. This guide is a summary of best practices for exoplanet observing, as well as it contains a written step-by-step guide through the same sample observation of WASP-12 that we will be covering in this video. So we ask that you also download that guide so you have that also as a handy reference. Also on astrodentist.com, you will find the calibration files and the science images of WASP-12b that we will be using as an example throughout the rest of this video. And again, we ask that you download those zip files and install them on your computer so that as we're going through a step-by-step example in the video, you can follow along using the same set of calibration and image files. After you've downloaded the guide from astrodentist.com, we also suggest that you then print and have handy Appendix A of the guide. Appendix A is a worksheet that will provide useful information as we go through the WASP-12 analysis. Next, we suggest that you also set up a directory structure on your computer where the bias, darks, flats, and science images will be stored in separate subdirectories. Here you see an example. The main directory is WASP-12, and what I'm showing here are 5 subdirectories, one containing the analysis that will take place during the operation of AstroImageJ. We're showing 3 directories here where the bias files are shown, as you see here, as well as the darks and the flats and the science images. So if you could go ahead and set up on your computer a directory structure very similar to this with these 5 directories, and then you'll be able to follow in detail the example throughout the rest of this video. So having installed AstroImageJ, you'll probably see an icon such as this on your desktop. So if you could go ahead and double click that icon, what you'll see is the main menu for AstroImageJ. AstroImageJ is actually derived from a piece of software called ImageJ, and the options for ImageJ are to the left of this star field. So these are all the different options for ImageJ. We will not be talking much about ImageJ, so there's no need to go through those at this point. AstroImageJ is enabled by clicking on this star field, and the options available for AstroImageJ are to the right of the star field, which are the ones we'll mostly be concerned about. So let's go through some fundamentals of AstroImageJ before we get into the analysis. Let's first start with bringing up an image, one of our science images, using AstroImageJ. Very simply, one goes to File, clicking on File, and then Open. And then let's select under Science Images, where we had downloaded the science images of our sample observation. Let's just double click on the first image. as you see here. And up comes an image display of the image. A couple of things to point out. If you take a look at there's the coordinate systems, ImageJ X, ImageJ Y, and the second coordinate system, fits X and fits Y. This display shows coordinates in both forms. The standard form fits X, Y is here to show you the standard fits X and Y coordinates, but also the ImageJ X and Y coordinates are also shown, which do differ. So for example, for ImageJ X and Y, the 0, 0 coordinate is in the lower left here. As you see, the numbers up here change. And the coordinates for the fits X and Y 0, 0 is, in this case, in the upper left. Now, these 0, 0 coordinate systems for each either fits or ImageJ will change depending upon the orientation of the image. Here we see that the x-axis, and this represents the x-axis of the CCD chip, is in this direction with the y-axis here. We'll see in a minute how one can flip and rotate the image, and in doing so, the coordinate systems will change. There's really no need at this point to worry about the coordinate systems. We're just reviewing this for information purposes. Now, some of the items that are important are what you see here in the header: value, peak, and integrated counts. As I move my cursor with the crosshairs and the concentric circles over a star, you'll see how these values, peak and integrated counts, change. So let's move it over this particular star here. What you see is I make small movements. Peak does not change very much, but value and integrated counts do. Peak is the maximum ADU count in the inner aperture circle. That's why it doesn't change as I make small movements. Value is the ADU count of the pixel that I happen to be on at that point in time. And integrated counts are the ADU counts that are computed in the aperture after the sky background is taken into consideration. And we'll cover later how one defines these concentric circles, that is to say the aperture and the annulus. Now, to see these values in a little bit more detail, let's zoom in on this image. And one easy way of doing it is if you have a mouse with a wheel, just turn the wheel as you zoom in. Let's zoom in all the way to individual pixels. And as I move my cursor in the crosshairs, you see, for example, the value of this particular pixel is 1,622 ADUs. And as I move in my aperture, you see that again, the peak stays the same, but the value of individual pixels and the integrated counts do change. All right, so let's zoom back out where we were before, roughly. And now let's take a look at some of the indicators that you see here. This particular image has not been plate solved. That is to say, ImageJ does not know the right ascension and deck coordinates, nor the orientation of this image. So the values here for, in particular, east and north are not necessarily valid values until we plate solve, which we'll cover later. Putting any credence on these east and north values indicators are not appropriate. But X does indicate the X direction of the CCD chip, and Y the vertical direction of the CCD chip. The other values that you see here, 3.8 arc minutes, for example, represent the width of this particular scale here. Now, this again is dependent upon the pixel scale of this particular CCD chip. And again, unless this image is plate solved, which at this point it is not, it's important to set the image scale so that these numbers are accurate. This information is only used for display purposes, not used in any calculation, but it is convenient to get these numbers correct. And the way to do that is to go up to WCS, which refers to World Coordinate System. And if WCS, that's to say, if this image has not been plate solved, then it's important to set the pixel scale for your images. And then in this case, the pixel scale is 0.62 arc seconds per pixel in both directions, since the pixels on the CCD detector are square. Having said that, then this scale does represent pretty accurately the width in the X direction and the Y direction. Now let's explore some other options on the image display. We go to the Files section. There's a number of options for saving the display here in different ways. The one that we'll mostly just focus on is saving the image as either a PNG or a JPEG. So by clicking on this particular option and going to, let's say, the AIJ analysis, one can store a file, let's call it sample image, and save it, and then that will save it in that directory. So if you wanted to save later, as we actually put aperture and annulus concentric circles on the star field, that would be a convenient way of saving such an image. Preferences, the only option I think it's worth staying at this point as far as preferences is this option, display mean counts in aperture. That's to say, the value in this field here, which, as we said earlier, represents the maximum ADU count in the aperture. One can change the meaning of that by clicking on this preference, and then instead of this representing the peak, it represents the mean of the ADU counts. So let's just set that back to covering the peak. And that's about the only option under preference that we'll cover at this point. Under view, one of the important options is the ability to change the orientation of the image. So we can change, for example, we can invert X or invert Y. In this case, X is inverted. We can change the orientation of the image by selecting these different options. And you can play around with this to see how that affects the image display. Next, an important feature under Edit is to take a look at, allows us to take a look at the FITS headers of this particular image file. So let's go ahead and do that. So if we click on FITS header, what we see are the different keywords in the FITS header and their value. And there's some important ones that we should point out here. One is, of course, the exposure time of the image. This confirms that this image was taken with an exposure time of 45 seconds. The other important keywords in the FITS header, and some image capture software put them in and some don't. So it's important to understand in the FITS headers that are produced by your image capture software, if the following keywords are in fact already computed. One is air mass, as you see here, which is an indication of the air mass that was in place or was true at the time this image was taken. The next two are the latitude and longitude, site lat and sat long, of your observing site. Now, one little quirk here that we'll show how we can take care of later is that in the case of at least SkyX Pro, which is the image capture software that is used in this analysis, you'll notice that the longitude is a positive number, even though we know that the location where this was taken place should actually be minus 76 degrees. So we'll see how, when we're doing an analysis using AIJ, how AIJ is able to negate or take into consideration the fact that the longitude by the image capture computer is of the wrong sign. So again, when you're looking at the FITS header of your image capture software, it's important to identify whether this particular quirk is true or not of your image capture software. The last two important pieces of, last two important keywords are the object right ascension and object deck keywords. And as you see here, these are indicated correctly for this particular image capture. So prior to an actual analysis, it's important to make sure that you understand which keywords, as the ones I described, are in your FITS headers, or if they're not, we'll see how they can be included in the FITS header. Okay, now let's go back to the header in the image display that AIJ is showing for this particular FIT image. Another option that it's important to understand is under Analyze, the Plot Seeing Profile option. What this option allows us to do, as we'll show here, let's put our cursor over a valid star here, and let's just put it over a star and click left once. Then let's go to Analyze, and what we'll see is a plot of ADU counts distributed across the aperture. This shows the profile, if you will, of the point spread function of the star. You see how it rises. This is, of course, half of the width of the area of the location from the center to a radius here of 9 pixels. And this shows us the full width half maximum in pixels for the star. And also it gives suggested radius of the inner aperture. In this case, it's suggesting a radius of 9 pixels. And it also suggests for us what the band for the annulus should be. In this case, it's suggesting beginning at 16 pixels from the centroid of the star out to 24 pixels. So at this point, it's important to record these values because we can use these values as the initial values for our aperture and annulus. And lastly, let's take a look at, again, the WCS option. If we wanted to actually do a plate solving, and we'll cover this later, there is an option for doing it using astrometry.net, either the online version or now in the latest versions of AstroImageJ, there's the ability to do plate solving locally, and we'll cover that later. Okay, now let's close this image down and let's take a look at another option under File, which is the ability to import multiple images. So here we go to the Import option, Image Sequence, and let's go back to our Science Image subdirectory. And in a given subdirectory, we click on any image in that subdirectory, not a range of images, but one image. And then when we hit the Open tab, this dialog box comes up and says that we have 336 images in that directory. Note that for Mac users wishing to import a set of files,
the subfolder should be selected versus a single file?
We have a couple of options before we display. One is to be able to sort them, the names numerically, which we'll just keep checked here, but also whether the images should be put in a virtual stack or loaded up in memory. And with a large number of images, let's just keep this checked as using a virtual stack. When we hit OK, the images are all loaded up, and we now have all of the images, the 336 images of our WASP-12b analysis loaded up. Now, the image display looks very similar to what we saw for an individual image, except we also have on the bottom this play button, where we can actually, by hitting the play button, cycle through all of the images, as you see happening here. Or we can take the slider and actually walk through the images. Now, one thing you'll see in this observation that, of course, is very important in terms of best practices, you see very little movement on the CCD detector of the star image field. And as far as best practices, this is very important to do so that if the flat fielding that was done is not done uniformly, which is never perfectly possible to get a perfect flat field, then it's possible for, if there is some movement, for a star to move on to a dust mode, and this could arbitrarily change the brightness of a star. So you see this image is pretty well centered and doesn't change very much from image to image. Very little movement on the CCD detector. So going through the images in this fashion, one also sees changes up here, a couple of different numbers. What you see here changing, for example, 134 indicates this is slice 134 out of 336. Now, a slice is in AstroImageJ the number of the image in its loaded up image stack. It turns out, almost coincidentally in this case, that the image number here or the slice number 134 corresponds to the numerical number of the image name. If I had deleted some images, let's say because I had some bad images, then these counts would not be the same, because this represents the fixed part of the file name, whereas this represents the current slice in AstroImageJ's stack. But you can see as I move through the images, the slice number changes, in fact, all the way up to 336. So that concludes this introductory part of the module to AstroImageJ. And in the next part, we'll be going through how the calibration files that we've collected can be used to create masters and ultimately calibrate the science images.